So we've looked at calculating the area under a curve, but what if we take this a little bit further and look at calculating the area between a curve and a straight line, or just two curves, two generic curves on a plane? We have to be able to do this effectively and efficiently and be able to calculate that space gap between the two of them. Now I'll show you what I mean. What I mean is, if we set up a scenario like this, so if I've got two functions, so if I've got one function, a curve given by f of x here, and I've got another curve given by g of x, so in this case the curve is a straight line, or in this one here I've got a curve given by f of x and another curve here given by g of x. So I've got these curves and they intersect at these points, a and b in this case. Now what I want to calculate is the area between them. So for this one, what I'm talking about is the area in this gap here. And for this one, I'm talking about the area in this gap here. Now, we have to come up with an effective method of doing this. Think back to when you did shapes. Think back to when you had something like a rectangle with a bit cut out the centre. And you had to calculate the area of something like this. Now, in order to do that, we calculated the area of the big square, the area of the wee square, and we subtracted them. So we took the big overall area and subtracted them. Well, when we are doing something like this, the same logic applies. Now, what we want to do is calculate the overall area from A to B of the outside one, i.e. the big one, which you'd substitute as our big box. So in this case, it would be the overall area of the f of x, because that would give me the overall area of the entire thing. Like we did with this one, we'd then calculate the area of the middle bit, the part that we wanted to get rid of. And in this case, that would be the area here, so the area under the curve g of x. What I would then do is the same logic here, subtract this area off the big area. Now the same logic applies here. If you look at this one, I would calculate the entire area, so that's this top curve, g of x, and I'd then calculate the area of the f of x, the area underneath this one, and I'd subtract them from each other. So essentially what I'm doing is area of the top curve, take away the area of the bottom curve, and that's the logic we have to do. So what we want to then do is to calculate the area between two curves from the points A and B, the points where they intersect. What we have to do is the integral of the top curve take away the bottom curve with respect to x. So we have to calculate that area. We first have to do top curve minus bottom curve to get our equation that we're going to use. We then have to integrate from A to B, i.e. the 2 points where they intersect. Now this is a fairly straightforward concept to understand. Looking at this, actually it's quite easy. But there is a wee tweak that you've got to realise. And that wee tweak is something like this. So if we've got a curve like f of x, where part of it is above g of x and part of it is below, we have to make sure that we split this in. Now, it's the same logic as if we were integrating a curve that went above and below the x-axis. We'd split it so anything above it was calculated in one integral, anything below it was calculated in another. We'd then combine the areas. We have to do the same sort of thing because we want the area here and the area here. But you'll notice the top curve in this section is different from the top curve in this section. So what I'd have to do is I'd have to get a point here called C, where they intersect here in the sign switch, and I'd have to split it into two integrals. So if we've got one like this, where the top curve changes at any point, let's go with f of x and g of x being our generic curves, and I have to do the integral of the first section, so a to c, of the top take away the bottom. Now in this case, the top is the f of x, the bottom is the g of x, all with respect to x, our dx there. I then have to do the area of this part and add them together. So I then have to add the area from C to B of the top take with the bottom. The only difference here now is the top is the g of x. So it would then be g of x take away the f of x. So I've switched round the way in which I do the curves, because now the top one is a totally different curve. I have to combine them a totally different way. So I'd have to make sure for the total area, which I'm going to call a of x, I would do this. I'd switch my integral around and I'd make sure I always did top take away the bottom. Right, I'm going to show you an example of this. So I want to calculate the area between two curves, y equals x bracket 3 minus x and y equals x, so the straight line there. So this would look something like this. So I've got a quadratic here, y equals x bracket 3 minus x. So it would be a curve that looks like this, and it would be a straight line there. So I'd have to calculate the area here between the two curves. Now, a key point, it crosses the x-axis here, yet, but I just have to do the same standard integral, so top take away the bottom, and it'll take this into account. First thing I need to calculate is the points of intersection, so I have to say, right, so x bracket 3 minus x equals x, what are the points there? Multiply this out and shift this one over, I get 3x minus x squared equals x, so I get 2x minus x squared equals 0. Factorise it and solve, I get x bracket 2 minus x is equal to 0, so I get my points of intersection being 0 and 2 for x. So there's my 0, and this one here will be at 2. So I know the limits for my integral, now I can have a go. So I know my integral is going to go from 0 to 2, of the top take away the bottom. Now the top is the x, so the top is y equals x, so it's going to be x take away the bottom, which is x bracket 3 minus x dx, all with respect to x. So what I do is I multiply out the bracket here, and then I can simplify what's in the bracket here and get an equation to solve. So I've got x take away, well, that'll give me 3x. It's then minus x squared, so plus x squared dx. That simplifies to the integral from 0 to 2 of x squared minus 2x dx, all with respect to x. So now I just calculate the integral, and that gives me the total area between my curves. Integrate it, I get x cubed over 3, take away 2x squared over 2, from 0 to 2. So that then gives me, again, substitute the top and then the bottom, 2 cubed over 3, take away 2 times 2 squared over 2 for the upper limit, minus 0 cubed over 3, take away 2 times 0 squared over 2. Now this one just disappears. All of it is 0 to the power of something multiplied by 0, that just goes. First bracket here, 2 cubed over 3 then gives me 8 over 3. This one here, 2 times 2 squared divided by 2, well 2 squared is 4, times by 2 is 8, divided by 2, we get take away 4. What I then do is do 8 over 3 take away 4, well 4 is 12 over 3, so 8 over 3 take away 12 over 3 gives me negative 4 over 3. Again, it's negative, I can't have a negative area, so my total area is 4/3 units squared. There you go, the total area between my two curves is 4/3 units squared. So we've used these steps to calculate it. We've used these generic steps to be able to calculate the integral between the two curves. Points of intersection, top take away the bottom, integrate between the 2 points, and then you're done. Bear it in mind when you're doing that, and you'll have no issues with these. Again, remember, if it switches which curve's the top, which curve's the bottom, you switch the order in which you do top take away the bottom for a second, or a third, or a fourth integral. It depends how many times it switches.